All right, good morning. So I just came from Scandinavia. I'm an adept of colder climates, and so I'm a bit overheating right now. But anyway, good. So this morning we'll talk to you about systems with a lot of interfaces. You'll hear about foams and emulsions. I will only talk about the interface. So for the last 10, 15 years of my life, I've been interested in a boundary condition. And that's been entertaining me quite a bit. That's all. So I have very limited ambitions. What you see here, and this we'll discuss on Monday, this is actually a film of Westmalle triple Belgian beer, thinning before coalescence. And you see protein aggregates, etc. But you'll have to wait to Monday for that. Today I want to talk about interfacial rheology. Gareth has introduced you to the concepts in rheology. We'll do much the same for an interface, but an interface is annoying because it's compressible. In bulk materials, liquids in particular, we can assume incompressibility. So we can throw the equation of state out of the window. Pressure is ill-defined, extra precious matters. But an interface deforms, luckily so. We couldn't breathe otherwise. And so this will mean that the mechanics are a little bit more convoluted. And we have to separate effects of compressibility, changes of thermodynamics, transport phenomena from rheology. And so we'll see how we do that. So I'll spend some time on the concepts of mechanics of interfaces. We'll use the realm of continuum mechanics, which is a beautiful coarse graining method, and we'll think about those things. And then we'll specifically focus on how to measure things and what can go wrong. And the answer is, again, a lot. Anyway, good. I need to thank these colleagues, some of which are former students or postdocs, which helped to bring together these slides in the way that we teach this, because they always said that I was too confusing and going too fast and not explaining things enough, and they were probably right. But so they've helped a lot, Mariana in particular, and then Manolis. And then I worked on this with Jerry Fuller for many years and profited a lot from discussions with Hans Christian Oettinger about non-equilibrium thermodynamics, and he always asked me, where is the interface? And that's the first question we'll tackle. But okay, what do we want to do and why do we want to do this? We can use interfaces and the rheology of interfaces, the mechanics of interfaces, to stabilize high interface systems in ways that are different from classical surfactants. And you've probably heard about Pickering emulsions. Here you see Pickering emulsions stabilized with some graphene oxide particles. I could have used a protein example, but what you see here are droplets stabilized by platelets of graphene oxide, and you see that the droplets are not spherical. Okay? So somehow the interface is able to accommodate the differences in pressure that occur due to the differences in curvature. There's also beautiful work from Paul Clegg and Mike Cates on using interfacial rheology to arrest phase separation and make materials that, by the interface itself, they're fully liquid except for the interface, which creates a scaffold and holds it. And these are called bigels, bicontinuous gels and emulsions. And the funny thing is, for example, for these graphene oxides, you could stabilize with the same thing, water in oil and oil in water, because you don't rely on chemical affinity, but you just rely on some kind of skin that forms at the interface. Another area that I like was work with the experts of this, Stefan Dorbolo and Benoit Scheidt, antibubbles. It's just a cool word, right? So you drop a droplet in the liquid, and if it's surfactant on the interface or something rheologically active, you can make a liquid air shell liquid system. And that's called an antibubble. And for imaging applications, that can be very useful because you put less air in a body, which is a good thing because you can die otherwise. And then, of course, there's coalescence that we want to influence in foams and emulsions. When I bring two interfaces together, the stress boundary condition here dictates the flow in the thin liquid layer. If there is only surface tension, the interface cannot carry any tangential stress. If there is stuff, in this case particles, that interact laterally, and I form a skin, I form like a pipe. There's a solid wall, and I have slower flow. And so drainage is an important step. Okay, an area where I'm interested in working currently is on your lungs. Your lungs stay open, not just because your surface tension is low. It is low, but not zero. It's 25 millinewton meters in the lung. There's a lipid mixture, DPPC, DOPC, cholesterol, etc., that lines the walls of the structures deep in your lungs, the alveoli. And these are very small bubbles, if you want. And so to prevent collapse when you exhale, when you compress, there needs to be a force pushing back. And that force is not coming from the tissue. Elastin is not strong enough to do that, but it's coming from the lipid layer at the interface. So there's interfacial rheology. And so we've been looking at diseases, for example, when babies are born prematurely, you can inject this lung surfactant, and it has to coat the lungs, and you have to form a homogeneous thing. This is, medical stuff, so there's a lot of money, so they make videos for you. Also during COVID, and this is work out of Minnesota, when lungs collapse, it's because the lung surfactant doesn't work anymore. And the inflammation products, that basically what you get is phospholipids have a glycerol bond. It gets attacked by inflammation, and it breaks up into fatty acids. And then you get things that are far less rheologically active. They are still surface active, but not able to resist compression. And what happens is your lungs collapse, your alveoli, and your lungs fill up with liquid. And this is the thing with COVID. Beer. I'm a Belgian, not Swiss yet. Proud Belgian, and of course we like our beers to be foamy, and we'll talk about that. And beer is a wonderful example. This is Westmalle. It's a triple from 20 kilometers from where I was born. And when you look at the processes that go on in foams, and I'm sure Arnaud will talk about that, you have oswald ripening, you have coalescence. There's a lot of interface deformation happening. And if you are from a civilized country and you like foam on beer, sorry, Gareth, sorry, then you want to have surface rheology. And my dream, my hopes and dreams, as Maria, one of my students would say, was that I could tell the story that interfacial rheology is all determining in Westmalle triple stability, but it's not. But again, we'll see that on Monday. And I was very motivated to get this because some of the trappists are very hard to get. This is Westvleteren. It's a trappist you can only buy at the monastery. You have to order, and it's ranked consistently because it's so scarce. It's ranked very high in the best beers of the world rating, which are a bit, it's a Belgian putting them together, so there's all Belgian beers. But this one often ranks number one. But you cannot get it in the supermarket. You cannot get it in the shop. You have to go to and it's very hard. You have to call, reserve, and they're always sold out. And so at some point I said, I have an idea. I mean, they have sometimes a problem that if they have a fungus in the beer, that creates a protein called hydrophobin class 2 protein. It's a protein with 2 hydrophobic patches. It barely affects surface tension, but it forms a network at the interface. It's like a Mickey Mouse molecule, and the little ears all get together and form a network at the interface. And it forms a very elastic skin. And so every bubble that nucleates stays stable. And so you get a phenomenon known as gushing. If you open then the bottle that you preciously got from the abbey, you get a meter of foam shooting out. And so I told them, we can fix this for you. Send me some sample, and they send me 3 milligrams of the protein, not the beer. And the solution is very easy. You have to add some hop oils, and then you screen the hydrophobic interactions. Anyway, good. So I hope you're motivated to get to interfacial rheology. It can get you some protein, and that's nice. But the question is, what's an interface? So this was the question my colleague Hans Christian Oettinger, who's a deep thinker, always asked me, where is the interface, right? And Emanuela can see him asking it, where is the interface? Every student that had a research plan defense, he would ask the same question. Interfaces are, of course, things which we construct in our mind, right? In a real system, I have a gradient in density at the interface. I have molecules leaving the interface, coming back. I have a gradient in density at that interface, and I have thermal fluctuations which make the interface corrugated. What we will do is, if we have water and air, for example, we will basically take, an average. We can still take into account the density variations in the liquid, and I could describe this with thermodynamics. And I could have a separate thermodynamic description of the interfacial region, and I could have an interface, right, which is thermodynamic phase. And this is what Guggenheim does. The problem is this gets mathematically extremely complicated because you get so many thermodynamic variables that you have to follow, etc. We will treat the interface as discontinuous, and the roughness of water is only 2.4 angstrom, which we will neglect, right? If you balance the surface tension, flattening the fluctuations with a thermal energy that drives the fluctuations, you find that's 2 angstrom. So we will do a sharp interface, okay? And we will ascribe properties to that interface. Surface energy per unit area, known as surface tension, right? We do that, you learned in undergraduate physics. We can describe a surface temperature. We can describe a surface viscosity to an interface that has no thickness. But it's okay. That's how we describe it. It gets even worse when we go to real interfaces. Here's an interface at the wall of a cell, for example, phospholipid bilayer. It's a few nanometer in thickness. You have two phospholipids happily together, merged. It has a finite thickness, the length scales, but still, in fluid mechanics, we will most of the time describe this as a sharp interface with no thickness, but we will ascribe properties to it. And this was introduced by Gibbs long time ago in his treatise, which is, I have his articles, they're unreadable, but Lewis then transformed it into something understandable, but he really has that all in there. So, and he talks about dividing surfaces. Really, I divide my two bulk materials, and then I have an interface which has to do the job, that it has to have the boundary condition to match what goes on into these two things. But it's a bit of an iffy thing, and again, my question the question Hans Christian always asks is, where is the interface? I mean, because the interface is an arbitrarily chosen position. I decide where it is. I have Gibbs degrees of freedom. I have to give one up when I decide to have an interface, and this means I make a choice. And I can make this choice by the discontinuity in temperature, or concentration of ethanol in my beer, or I could take the average density, or I could, so there's a number of concentration fields, temperature fields, and density fields are living in that interface, and where I put that interface is my choice and will determine how I will do things. For fluid mechanic applications, and for applications in transport phenomena, we're most of the time going to choose the excess density so the density difference, the average density between the two liquids, I'm going to set that density, excess density relative to that to 0. And I choose my interface to be there, okay? And this is a choice I make, and by that, I can write now all the balance equations. But for example, the temperature discontinuity does not need to be in the same field. The concentration of species, if I have 5, 6 components, they all live in that interface, but not, at the same. And this can make things complicated. If you have transient systems where you have diffusion to and from the interface, or if you have non-isothermal systems, you have to be extremely careful how you do that. Today, I will only talk about so-called passive interfaces where I don't have these concentration fields and temperature fields living because it makes my life too complicated. But when they do, you have to solve additional partial differential equations that describe that evolution of that relative to the interface that you follow, okay? But because we do fluid mechanics, it's a choice that we make and that we can do. And so these active interfaces are not active in the bug stuff kind of thing, but they're active in the sense that they move and that you have a number of, and the gradients are very steep. So this is something which and so what Hans Christian introduced was like in quantum mechanics, gauge transformation. So what happens when you move the interface? The beautiful thing, which is fortunate, is that all the thermodynamic relations between the variables that you define stay the same. But the absolute values are different. So you have to be very well aware of the question, where is the interface? The interface is, for us, in fluid mechanics, rheology, mechanics, emulsions, it is at a place where the excess density is 0. And that's what we follow, and that's what we use to set up our equations. If you do non-isothermal stuff, you're braver than me. I stay away from this for now. Maybe I'll do it at one day. Yeah, good. So we have an interface. We define it by excess density being 0, so the average density between the two phases. That's what we follow, and then we see what happens. And then we have to look at continuum mechanics. So just to get you accustomed to my notation, I will just give the bulk equations first. I have the continuity equation, the change of density in time, and then I have the nabla, and then rho times u, the velocity. Most of the time we happily ignore this. We can use the Stokes equations because the density is constant. Density is constant means things are incompressible. We can throw out thermodynamics. Pressure is ill-defined. That's what we do when we solve the Stokes equation. We only care about extra pressure differences, normal stress differences, shear stresses. We don't care about the pressure in the equation of state. This will not be able to do for interfaces because incompressibility will not be a given, right? So this means that we will have to solve the equation of state and we'll have to look at thermodynamics and mechanics at the same time. And they mix. When I compress something and I change the concentration, I will have a resistance. This is not the mechanical stresses that I have when I take a solid piece of material and I compress it. This is a change of the thermodynamic state. And so I will have to take it into account. And so then for my bulk phases, I have the Navier-Stokes equations. Usually inertia will not be much of an issue. We typically will have Stokes equations, or maybe for foams we have the Inviscid equations, but we have the Navier-Stokes equations. The material property is the bulk shear viscosity. We neglect the dilatational viscosity here. Okay, good. So now I take this situation. I have two fluids, an emulsion or a foam. I have my governing equations, which are the Navier-Stokes equations in both phases. I can simplify them to Stokes equations, blah, 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 blah. And then I have the interface. And what the interface needs to do, it needs to balance the stress difference between the two interfaces. For example, you have a bubble. There's pressure inside, which is higher than outside. The interface needs to be able to accommodate that stress differences by having a surface tension, right? You have Laplace law, and that's something we'll do. But we write it here more general. I have phase 1, I have phase 2, and then I have my interface. First, I can write the continuity equation. The velocities need to be continuous, tangential components, normal components. I will, from now on, forget about the interface itself being able to have a velocity. We'll just say that the interface is not moving, but be aware you can do the whole mathematics, the whole framework with the interface itself moving. If you have a mixing flow, for example, that can be the case. The thing is, I want to write a stress balance over this interface. So the interface, there's a stress difference between fluid 1 and fluid 2 projected onto the interface, acting on this area A, and it must be balanced by a surface stress at the interface acting on the traction vector here lying in the interface. So this surface integral needs to be balanced by this integral, the stresses in the interface. Surface tension, for example, for a bubble. This is a very complicated way of writing young Laplace, okay? I can convert a contour integral into a surface integral by using Gauss divergence theorem, and I get this equation. And then because it has to hold for every surface and every contour, I can get to an equation that simplifies to a stress balance equation. I have the stresses, the momentum from phase 1, the stresses, the momentum from phase 2, and they must be balanced by this gradient of the surface stress, okay? And what is this surface stress? This surface stress is a simple thing. It's a tensor, 2 by 2. I have 4 components. I have axial components that resist compression dilation, and I have shear components that resist area changes, shape changes. And I have an isotropic term, that is the surface tension, or the interfacial tension, and that's a function of the surface concentration and temperature, and IS is the surface identity tensor. I do it here for planar interfaces. You can define this for curved interfaces. It's a bit of a mess. You need to do differential geometry. Projections and keeping track of what happens is a mess. You will find papers where things go wrong. This is a tricky thing to do. But you have an isotropic thing, meaning I have a surface tension, and of the identity tensor, I only have the on-axis components. So this is the same as a pressure in bulk. Surface tension is an isotropic stress. It works only along the diagonal axis, and it's the same regardless of this. And then I can have extra stresses, like in rheology, bulk rheology, that when I try to change the shape of the object, I will get shear resistance. If I change the area, in addition to the surface tension terms, I can also get mechanical resistance too. For example, if I make a particle-laden interface and I compress the particles, I will have a mechanical stress fighting that. So the stress tensor at the interface has isotropic components, surface tension, and has extra tensors like that. And it's the same as in bulk. And so if I look at my contour on my interface, and I have this surface stress tensor now acting, I will see that it acts in different ways. So here I have the stresses acting on the bulk. I have viscosity of bulk phase 1. D is the rate of deformation tensor, dvx dy, right? Shear rate. For example, for a shear flow, I have the stresses in phase 2. They don't need to be the same. If I have a solid interface, there can be a velocity difference between my two phases. Fine, my interface can deal with that. If I have a viscous interface, it can create a discontinuity in velocity. That's what the interface, that's what we're trying to engineer, because it's a good thing to slow drainage down. So this is the bulk stress. I can have differences in pressure. If I have no flow, for example, this will be Laplace. And then, sorry, this should not be here. And then I have 3 contributions that the interface can generate to stop that. This one, which looks the most complicated, is actually the one that you know best. N is the unit vector, nabla S is the surface Laplacian, and this dictates curvature, right? So this is a complicated way of writing curvature, tensorial. And so this is the Laplace contribution, capillarity. This is gradients in surface tension. We'll see what this means. Gibbs and Marangoni stresses. And then this is truly interfacial rheology. Okay, so let's look at these different contributions to the interfacial stress, right? So we'll see how they are coming about. We'll see how they're engineered, how we formulate them. So the interfacial stress tensor is a two-dimensional tensor. It has 4 elements, 2 on-diagonal components, 2 off-diagonal components, shear stress components, normal stress components. The pressure term is isotropic. We can have normal stress differences at interfaces. Nobody's measured them yet. Could be a fun thing to do. I don't know if you want to, but yeah. Then I have the interfacial tension, right? Which you know from your intuition and undergraduate physics. It's the energy needed to create interfacial area. It's a thermodynamic. You're fighting thermodynamics. And it's a scalar. It can be position dependent. It can be time dependent. You do adsorption, desorption. But the key thing, it's a thermodynamic property. It's a state variable, right? So in principle, if I know the state of my system, I can calculate it. And if I have a system that is simple and has no big molecules, but has, for example, alcohol molecules that are not very strongly interacting, and I change the area of my interface, I will change the surface concentration, I will change the state of my system, I know exactly what I get. So this is governed by thermodynamics and by the state of the system alone, okay? And then I have my rheological stresses, my extra stresses. They come from, structure at the interface, proteins interacting, the hydrophobins, for example, and they give you mechanics. They give resistance to shear, solid-like properties, right? If I get a shear modulus, I get solid-like nature, and they can be everything that Gareth promised you. They can be time-dependent, can be rate-dependent, can be strain shifting, everything. So there's a lot of fun to play with. They are given by constitutive relations, right? We have, and there's a lot of work, I think, still to be done on molecular modeling of these systems, but they are given by empirical relations, constitutive relations that relate stress, now not with a thermodynamic state, but with deformation or rate of deformation. Okay, let's see some examples, okay? I'll break it up. Here's the first one. Let's assume we have a system, water or water alcohol, that's relatively clean, okay? So the only contribution to the stress that I have is the surface tension, and there can be no gradients in surface tension. There can be no gradients in surface extra stress because there are no interactions. So the only contributions I have in a system, for example, without flow, is the pressure difference across the interface and then the curvature, okay? So I have a surface tension that is the one that you know from simple liquids. And we know how surface tension arises, right? We have molecules that are in the bulk, they're happily surrounded, have many, many friends. And then there are the ones that are at the edge, they have fewer friends, they're a bit unhappy, and this is the drawing you find in textbook. So I have a question for you, right? So this is an imbalance in stresses, but why is the surface tension horizontal and not pointing down? Because my molecule at the interface is like floating on the sea here. It's floating there, it's feeling the molecular interactions from below, but we always learn surface tension is horizontal, right? So why is surface tension a horizontal force? I mean, why is it horizontal, not pulling molecules down? Why is that? Yeah. Yeah, true. But then molecules just go in, and the molecule that sits here would again feel a pulling force, so we should get a very complicated thing at the interface. It's a subtle thing. The density in the interfacial region is slightly lower, right? Because I have molecules leaving the interface the whole time. So if I just take a simple molecular interacting system like a Lennard-Jones type system, the intermolecular distance is slightly bigger than the equilibrium molecular distance. So you're pulling the molecules out of their potential well. So these unhappy molecules, they feel a negative pressure at the interface because they're not in their equilibrium position, they're a little bit further away. And this is why you have this horizontal force. So it's a bit subtle, I think, yeah. But the consequences of this are very well known. When I have this stress condition over the interface, I have a stress jump, I can accommodate pressure differences, I will have a Laplace pressure inside a bubble, and I know very well what this is, okay? So the interface can give a tangential stress that balances the discontinuity in pressure. And this is very well known. Second case, I take a surfactant, small surfactants, very tiny ones, happy ones, right? They sit at the interface because of their chemical contrast. They float around. They don't have strong lateral interactions, so there's not going to be a lot of viscosity. There's not going to be a lot of elasticity. The only thing they do is they're happy at the interface. Now, if I have insoluble surfactants, I can change the surface concentration. How can I change the surface concentration? By changing the area, right? Or if I have a soluble surfactant and I'm fast, I will see the same. So here I have surface surfactants, and they can be a function of concentration. Concentration depends on area. If I increase the area, I will decrease the concentration. I will increase the surface tension, okay? So what does this mean? I will see an apparent elasticity, and this is measured a lot. It's called the Gibbs elasticity. In bulk, we would call this compressibility, or the modulus associated with that. And we have changes in surface concentration are brought about by changes in area, right? And I can measure that. Here's, for example, a beautiful part of history. Erwin Langmuir is famous. We call his, the thing he designed, the Langmuir trough. And he got the Nobel Prize for understanding that at interfaces, these densities are different and the molecular interactions are, you're very prone to seeing these molecular interactions. And that was what Langmuir realized. But he basically borrowed a technique that was designed by Agnes Pockels. Agnes Pockels was the sister of a physics professor, Pockels, from the Pockels effects in ferroelectricity, something like that. But she had to stay at home, take care of her parents, but she got all the books at home. Physical Review was already published at the time in Nature, and she would read them at home. And so she found an article by Rayleigh, Lord Rayleigh, kind of the god of his time. And Rayleigh had done an experiment where he had tried to determine the size of a molecule by spreading a layer of oil and trying to measure the thickness of a molecule by saying, I have this volume, I can measure volume accurately, I can measure area accurately. If I spread it on a pond, Clapham Pond, somewhere in London, he basically measured that and he used that to get an estimate of the size of a molecule. And Agnes Pockels said, well, this is very nicely done, and she wrote him a letter, but I can do better in my kitchen. And she said, instead of having an uncontrolled area, which is hard to measure, I will put a small amount, allow it to spread, and then basically try to see when I compress the interface so that I get that area. So she made the first Langmuir trough. So call the Langmuir trough Langmuir-Pockels trough. I mean, she really deserves our credit. Langmuir improved it and made many essays, but she was first. Also, nice note, she wrote a letter to Rayleigh basically saying, okay, it was a nice try, but I could do better in my kitchen. Rayleigh took her letter, sent it to Nature, and said, you should publish this. I mean, you can read it. And then she was really a fantastic scientist. She did wrote like 11 or 12, all very beautiful papers. Okay. And then Langmuir worked with Catherine Blodgett. Blodgett is for the deposition. Okay, cool. And so this was the device of Langmuir. He basically had barriers where he could control the area, and then he could measure through a balance the force acting on that barrier to measure the surface tension. And so it was a very clever construction. He also was avoiding leakage. I mean, beautifully done. I mean, I'm always amazed how these people in those days made beautiful experiments. But we can use such a, and this is what you can, it's what you can buy now. It's the only swimming pool in Zurich that you can afford, right, Peter? It's 20 centimeters. And but I have 3. But you basically have still the same system. You have a barrier, and then you dip a plate into the interface to measure the tension. And so you can then, for example, take a surface active molecule. This is from a review from Meuwel's group. And then as you compress that interface, you can measure the thermodynamics of that interface. So you start here with molecules in a gas phase. Then you get a gas to liquid transition, then you get a liquid to solid, and different solid phases depending on the details of the molecules and the kinks and the bands. And these are then 2D equations of state. And remember, I said for bulk, we can throw the equation of state out. For interfaces, we can't. If I stretch a droplet, I will move on this equation of state. So I will see effects of changing surface tension, in addition to possibly having rheology, in addition to possibly having desorption. And this makes life a little bit difficult. But for example, if I'm in this gaseous state, I can define, instead of thinking about a tension, I can define a pressure, because I want to make this analogy with 3D systems bigger. So I define a surface pressure as a surface tension of the clean interface, pure water, minus the surface tension of the dirty interface. And so this is a positive way of looking at interactions between molecules. So it's a 2D pressure, units Pascal meter, and the changes in pressure with area give you a response. If I have an equation of state, for example, Langmuir, I can calculate what is called the Gibbs, sorry, it should be 2 B's and 1 S. And I define it as K, because I'm trained as a mechanician in some way, and we call the shear modulus G, the compression or the bulk modulus K, and the Young's modulus E. The entire field of surface rheology calls this E. It's not a Young's modulus, and I think it's confusing, and I follow the nomenclature of the Society of Rheology, in part because I helped writing it. Anyway, but I think it's better to make the homology with bulk. It's a bulk modulus, it's a compression modulus. And what is it? Well, it's the change of surface pressure with area times area, or delta pi, delta L and A at constant temperature, pressure, and concentration. So this is a modulus that you can measure in a rheological experiment, but it's not a modulus in the sense that it relates from a deformation of the microstructure as we have in bulk rheology. It's a change of the thermodynamic state of the system that the system is reacting to. For example, if I do an experiment in these Langmuir troughs and I apply a strain, I will get a stress because I'm changing my interfacial tension, okay? So, and this is not truly a mechanical definition in the traditional sense. It's not a deformation of a structure, a strain. It's only dependent on the state variables. And so this is a thermodynamic thing. I don't even need to do the oscillations, right? If I measure my isotherm and I take the derivative, I take the slope, I have the same value. So this is good news. If you have the equation of state, if you know what your system is doing thermodynamically, you know the elastic response that you will get purely from the thermodynamics. But it's not a rheological material function in the strict sense, okay? So this is our first contribution. This beautiful work out of Unilever, long time ago. I was 4 years old. You were probably not yet born. Lucas and Van den Tempel, and they said, okay, if I now have this, if I have a system which is not, which is, you know, soluble, but soluble takes time. So if I go and deform very fast, equivalently the system is insoluble because I'm oscillating faster than the time scale to desorb. If I go slow, then the system is purely soluble. So if I go slow, there should be no frequency, there should be no response. And if I go fast, I should see the thermodynamic underlying state response. And this is essentially a system that looks like a Maxwell model, but it has a completely different meaning. It is related to the speed with which a material diffuses to and from the interface, okay? And then the underlying elasticity. Here's data for some surfactant. You get an elastic modulus. At high frequencies, it's constant, and it's related to the slope of the underlying isotherm. At low frequencies, the interface is continuously in equilibrium, so there is no lateral stress, and there is no elasticity to be seen, okay? And so you can measure in a very complicated way diffusivity. How? We'll see. Okay, good. How are we doing in time? All right, good. Then we go on. We're building complexity. Now I have a system which is insoluble. I have a surface concentration which varies with area strain, but the surface concentration can moreover vary with position. For example, we take a foam. You'll hear about foams. You have little thin films in the foam. Fluid drains out of these little thin films. The velocity in those films is not constant, okay? In the center of the films, this velocity is low. Here, it's very high, and then as you enter the plateau border, it changes again. So the hydrodynamic stress acting on these molecules changes with position. They are dragged along, the area is stretched, but the area is not stretched homogeneously. So I create a gradient in surface concentration, okay? So from the thermodynamic contribution, I can also get a stress which is known as the Marangoni stress. We will meet Carlo Marangoni later in the talk. He was an Italian scientist and worked, amongst other things, on the tears of wine, right? If you remember that, and that will come to that. But I can get a gradient in concentration that gives you varying surface tension with position, and it's a lateral stress acting because the surface tension here is much lower than here, so I have a force pulling the liquid back in, right? And that force depends on the equation of state, and I can get very complicated behaviors for this Marangoni stress. Finally, I can get systems with purely rheological functions. For example, I mean, if you go on the Mediterranean and you want to go fishing and it's stormy, what people will do is they will pour olive oil on the sea. I mean, they did in the old times, because then it would dampen the waves, right? You get a layer that is, in our approach, that layer, that's a viscous layer, but it does not like to be deformed. So you will get a purely viscous stress at the interface because of the olive oil that you put there. There's no big effects on surface tension. There's a little bit, etc., but you will get a purely mechanical stress. So I can balance stresses in the bulk liquids or differences in pressure by having this extra rheological stress. For example, ice cream. I have in ice creams, I have, Adam should tell me, I have a lot of stuff, right? Mainly air. Nestle sells a lot of air, I understand. I know, it's cheap. It's the only thing. Water is already expensive, but anyway. But then you have emulsifiers, you have fat globules, and you basically create a skin in the multi-phase system. You have an emulsion inside a foam. It's a very complicated system, right? Ice cream? It's hideously complicated. I mean, but the stability comes from surface rheology in that case, mainly because you get lateral interactions. And so we can get surface viscous systems, which then means I have a viscous stress. The viscous stress depends on how fast you go. For example, if you have a fatty acid, they're predominantly viscous. If you have proteins that interact, remember Mickey Mouse protein, hydrophobin 2, forms a network. That network will be an elastic solid. That is strain stiffening or strain softening, depending on the nature of the interactions. Or I can get polymer multilayers or layer by layer assembly, and I can get that, right? And then I can get everything together, right? I can get surface tension changes, I can get Gibbs elasticity, I can get Marangoni stresses and rheology and adsorption, desorption all at the same time. So it can be, depending on your view on life, a mess or a phenomenal challenge and an interesting field to work in, right? And you can deconvolute these contributions by going to the definitions. Everything related to thermodynamics, Gibbs, Marangoni, is related to the equation of state. It's a state variable. Everything related to transport phenomena, adsorption, desorption, Marangoni stresses will couple to the transport problems. So it will be related to length scales, and you can do scaling analysis as we've seen to understand how length scales influence that. Everything related to rheology is going to be dependent on strain, strain rate, and history. And so if you deconvolute this effect, I mean, thermodynamic contributions should be independent of strain, should be independent of geometry, of size. Transport problems, you make the things smaller, things will go faster. Strain is quite easily definable, and it's, you know, something that you can do. But it's fun. Okay, good. So that's the interface. The fact that it's compressible creates a lot of complexity, but also creates a lot of opportunities to design systems differently, and especially in food systems that can be very rich. All right, so I'll reiterate that a little bit. So we have our beautiful equations, and I apologize for the color scheme. This was done by Mariana, who's from South America and has a different color scheme sense than me. So she has bright colors, yellow and etc. So we have our surface stress tensor, and we have the thermodynamic aspect, right? The surface tension, which influences capillarity. If you have curved interfaces, that will act always. If you have bubbles, if you have foams, that will work. It can change by adsorption, it can decrease by desorption, right? If I compress an interface and I'm no longer in global thermodynamic equilibrium, I will desorb. So I can have a time dependence of my properties. That time dependence seems like viscoelasticity, and you can call it like that, but it's underlying a transport problem, okay? So it's not quite the same. Then we have this surface tension can be a function of position or time. So transport problems come into play. The adsorption, desorption to an interface, and there's been beautiful work done with models. How does, for example, a charged molecule diffuse to an interface that is already charged? And so you have models for the transport to and the desorption from interfaces. And then the Marangoni stresses, it means that if I have a flow, for example, I take a glass of Corsican wine, I'm not going to say more, it's probably high in alcohol, high in tannins, so you do the swirling, you get a film that forms. The alcohol evaporates from the sides faster, so you get a difference in surface concentration of the surface active alcohol on the walls and in the center, the surface tension being higher on the walls where there's fewer alcohol. So the thing is, the liquid gets pulled up by the surface tension, pulled up until there's a length scale of about 2 millimeter, gravitational length scale, and you get the tears of wine that are about 2 millimeter in size, right? And this is because I get a coupling between the surface flows and the bulk flows. I create a surface concentration gradient by a bulk flow. And this is something we'll have to worry about when we do experiments. And then I have rheology. I really have mechanical properties, structure property relations, viscosity, viscoelasticity, but they really come from non-dissipative and dissipative modes of structure deformation at the interface. And the problem is I will have to do both dilatational rheology, area changes. I will have to take the compressibility and the fact that I can do it, and this is, you know, designing basically the stability often relates to dilatational properties, and I have shear properties. If I want to distort the shape, I will have the deviatoric components of the stress tensor, sigma 1, 2, sigma 2, 1. If I have dilatational changes, I have sigma 1, 1, sigma 2, 2. So it depends what you do. So I will need to measure them separately because they are not going to be connected. Okay? Good. So let's look at how we describe that. Let's make some simple constitutive equations. Okay? This is a Newtonian interface. It looks very horrible, right? Newtonian interfaces were simple. It was sigma equals 2 times eta times the rate of deformation tensor, or sigma xy is proportional to viscosity times dvx dy. Here's the full equation, right? I have the surface stress, I have the pressure term, surface tension, isotropic, and then I have a term first that has this nabla s. Nabla is delta, partial derivative of the surface velocity with respect to position, delta vs to vx. It means this measures the divergence of the interface. This is the area change, and I need a viscosity that resists that area change. That is called the dilatational viscosity. We also have that in bulk. If you take a textbook on transport phenomena, fluid mechanics, you will find the same equations. We neglect bulk viscosity in bulk because bulk, this thing is often, the divergence of the velocity is often 0. We assume incompressibility. Only if you have fizzy drinks like Coca-Cola or whatever, you will need to take that into account. And then I have my classical term, 2 times eta d. D is the rate of deformation tensor, dvx, dy, dv as we've seen. And this is the shear viscosity. So I have a dilatational viscosity and a shear viscosity. They both come from the microstructure, but they're not uniquely related. Different microstructures give different values. It's like the Poisson coefficients. If you have different types of microstructures, if I have time, I will give you one example. They're not linked. For a given material, they are linked, but they're not uniformly linked. There is no thermodynamic relation between the dilatational viscosity kappa and the shear viscosity. And this was done by Skip Scriven at the University of Minnesota. Why did he care about that? He was working a lot on coating flows and stability of coating flows. And in coating flows, they also use surface active materials and rheological stresses to stabilize coating flows. Okay. And so I measure the resistance to deformation and dilatation, right? So shape changes, area changes, different things. Yes? This is because Newton fucked us over. Pardon, excuse me my French. Because the way Newton, yeah, you can write it differently. If you see here, if you do a purely dilatational flow, D is not 0. And you need to take out this part from D. Okay, that's why. If Newton would have written the equations properly, with you can write this nicer. With a dilatational part and a shear part separately, it would have been better. Yeah, thanks to Newton. Right. Yes. Yeah. Absolutely. It's absolutely the same. Yeah, exactly. But we are not used to of dealing with it, but it's absolutely there if you have gas flows. Solid mechanics people, they know Poisson coefficients, they know exactly, right? And we'll see that coming up again. We do solid mechanics here, right? So here's the equation, and we have a surface shear viscosity, and now it has funny units, right? Pascal second meter. Why? Because we decided where the interface was. We said it's a mathematically sharp interface with no length scale. We took the length scale out. And so it has a funny unit. It's because of the way we treat the problem, right? And we have a surface dilatational viscosity with the same units, okay? Then if we look at the bulk mechanics, it's the same, yeah? You have a shear, this is the surface displacement vector. You have a shape change, shear modulus, and you have a divergence. This should be a big U, sorry. This is a divergence, an area change. Area change, shape change, shear modulus, bulk modulus, right? Compression modulus. And the surface Young modulus is related like this. This is why I don't like E, like half of the world is publishing, because the software that does pendant drops gives you this. And there's people that initially did this work that were very careful, but then people that followed that work were not very careful. Anyway, just one of my little frustrations. You can write more complex equations, constitutive equations. This is a neo-Hookean. Did you talk about these things, Gareth? Right. This is rubber elasticity in 2D, right? So you have J is the determinant of the deformation tensor that measures area changes. And then B is the finger tensor, it measures shape changes. If you know what it is, you're happy. If you don't know what it is, just remember shape changes, area changes in a language that is a bit with tildes and stuff, right? But again, we get separate material functions, a compression modulus and a bulk modulus. There's also beautiful work by Dominique Barthez-Biesel where they do take into account the finite thickness and work with isochoric, and there's a whole set of constitutive equations depending on what you want to use that are really working well. Okay, so what did we learn from the constitutive equations? We have material functions in shear thinning, time, everything you want, moduli, creep, and we have those in dilation. Same thing, viscoelasticity in dilation. And so we'll have to be able to measure that. And so we'll start with interfacial shear rheology. Okay, famous Belgian, Joseph Plateau, right? Very good-looking fellow, as most Belgians are. He was a professor of physics at the then newly founded University of Ghent. He had done his PhD in Liège, Luttig, worked on solar spots, and got blind during his PhD. Turned out it's not as a heroic story as it seems. He just had an eye disease, but he was blind when he became a professor, and he had two mathematical problems he worked on. He was doing mathematical physics. One was minimal surface areas, so he did all these minimal structures, and you will hear maybe about Plateau's law a little bit in foams. So he really, and he used surface tension as a way to do experiments where you automatically minimize surface area. And he had his son-in-law doing his experiments, describing them, and Plateau did the theory. And then the second area where he worked was cameras, so for a blind one. And for many years, they named the film festival in Ghent the Plateau Film Festival. It tells you something about Belgian cinema when it's named after a blind. But Plateau was working together. He was a contemporary of Rayleigh and Young, and they worked a lot together, and they realized there was something special about interfaces, and then they worried about this interfacial tension, okay? And so Plateau at some point said there must be a viscosity associated with the interfaces. So Plateau did an experiment where he said, I take a compass needle floating on the interface, I pull it away from the Earth's magnetic field, and I let it go. So I do a creep experiment, okay? And he did that for a bare interface, clean interface, only surface tension, so there should be only the equation of motion of the compass, some inertia, blah, 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 and friction with the bulk. And then he put a surfactant there, saponin, a natural surfactant, poof. And he did the same, and he watched the needle was damped much, much more. So he was excited and said, I have discovered the surface viscosity. And he wrote a paper about it. Then this fellow, not so good looking, everybody knows Italians are less good looking than Belgians. Carlo Marangoni, contemporary, he did not agree. He said, well, when you're doing this needle thing, you're changing the surface concentration here because you're stretching the interface on one side, compressing on the other side. So you will have what he didn't call yet a Marangoni stress, but what we now call a Marangoni stress. I will get a lower concentration of surfactant here, a higher concentration here. So I have a higher surface tension here, so you pull the needle back. So, boo. And he said, I will do an experiment, much better, where I take a disc at the interface, I put the needle in a disc, and I do the same experiment, with and without saponin, and Marangoni did not see a difference at all, right? So he said, Marangoni said, you're full of crap. Surface viscosity does not exist. Okay, good. Lord Rayleigh came to the rescue. He said, that's interesting, a fight in the literature. We all like that, right? And so he started his paper in Nature, I think. The idea that liquids are endowed with a viscosity peculiar to the surface is found in the writings of Descartes and Rumford, so quite some time ago. And then blah, blah, blah. But it's to Plateau that its general acceptance is due. So he was team Plateau, right? So I like Rayleigh. And then he started to describe the discussion between Plateau and Rayleigh, and he said, let's do the experiment that's a bit more clean, because the disk is really not necessarily a good measurement, because the disk is in contact with the interface, but also a lot with the bulk, right? Most of the surface area of the disk is exposed to, if I deform that, is just doing what a Couette viscometer-like thing would do. So he said, let's make a ring. And I put a ring at the interface, and I will do the experiments. And now we'll see. And he said, okay, no interface dampens. With saponin, dampens even more. Plateau is correct. Good. But then he was a good experimentalist. He put a bar in the middle to mimic this Marangoni effect, and he saw that it was damped even more. So he said, well, Plateau was right, Marangoni was right, but most of all, Rayleigh was right. Yeah, that's. What do we learn for this about experiments? It means that when we try to measure a stress boundary condition, an interface, we don't want to measure the bulk, right? So we want something that's thin and long, like a needle or a ring, and that's what Rayleigh proposed. And there's a French mathematician, Boussinesq, who was first in Lille, then in Paris, who then did the first mathematical analysis of it and showed how bulk and interfacial contributions can then act as stress on an interface. And so we now call a non-dimensional number the Boussinesq number that says that the stress from the surface must dominate the stress from the bulk. So I have the surface viscosity for a viscous film, the velocity of the probe that decays over a certain length scale, the velocity gradient, acting on the parameter of my measurement object. And then I have on the bulk side the bulk viscosity, the velocity, which is probably the same, the length scale, which is probably the same, and the area. So the ratio of parameter per area will determine which ratio of viscosity you can measure, surface viscosity. And this has been a guidance for different experiments. And so different experiments have been made. Some people like the bicone, like my good friend Peter, because it's a very sturdy experiment, and Peter likes, very viscoelastic things. He likes protein interfaces and food systems. So for him, it's not too bad that there's a lot of interaction with the bulk, and he prefers to have a very rigid measuring tool. And so the bicone sits at the interface and makes contact here at a sharp edge and pins the interface, makes a horizontal interface, and no capillarity. We want to have only nabla s times tau extra, only that term, and that's what he measures. Devices that I like fluffier things, Peter. Is a device which is a rod rheometer, I'll explain in a second, or essentially Raleigh's device, the double wall ring, but with slightly improved flow conditions. So what are the devices? For example, the ISR has a magnetic needle floating at the interface, right? And there are two coils in Helmholtz condition, and then you alternate the currents and you wiggle, you create an alternating magnetic field, you apply stress to that probe, and with a microscope you measure the deformation. Stress, strain, I get viscosity, viscoelasticity. I can do this in creep, I can do this as oscillation. The thing is, this is not the friendliest experiment to do. The little needle has kind of a will of its own and floats around on the interface, and you can get very frustrated students. And then I usually go away from my lab and leave them alone. Yeah. And then the double wall ring is a tool that you can get from most rheometers, where you just connect it to the rotational rheometer, and now you use the whole sensitivity of a stress-controlled rheometer in particular, and you can do that, right? And you can combine that with, you need to be able to control the surface concentration, right? So you can combine it with troughs. This is, for example, work on Eline did on lung surfactants, where she designed then a trough, and we 3D print these rings and have openings so that you can control the surface pressure on both sides. Or we have solvent exchange cells that exist for the bicone or for the double wall ring, where you can, for example, have a protein. You can change pH, see how it denaturates, and then measure the development of the interfacial elasticity as a function of time. Okay, good. So this is a close-up view, and you can do that. There is, however, a bit of an issue. That is that the problem of if I have this rod, for example, at the interface, a rheometer has to have clean kinematics, right? We have cone plate to have a homogeneous shear rate in the sample. Here, when I move the needle, I don't decide where the momentum goes, right? The momentum can go at the interface, but it can also go down the bulk still. I mean, this was Raleigh's story. I mean, I coupled to the bulk flow. I've still have momentum diffusing away. So we'll have to be careful with the analysis, and we don't a priori know the velocity gradient at the probe. And I'll talk a bit about that anyway. So this is the current version of Much Smarter by Javi Tajuelo in UNED. He's basically built a system with a mobile magnetic trap. So they use a permanent magnet and now can wiggle the needle, and it's much improved. So, yes?
How do you control in your needle experiment this? Is it really critical to control the surface concentration?
Yeah.
What if you don't?
Then it sinks. Yeah. No. So you wanna know the thermodynamic state, right? So you wanna know where am I measuring the shear rheology? If I'm in the liquid state, or so you control the surface concentration either by adsorption, or by adsorption followed by a trigger of pH or whatever. You control the state of your interface, and then you measure. Or you combine it with a trough, where you compress. Or if you are very careful and you can spread. You have an insoluble serpent, and you can use a spreading from an alico. You can also control the surface concentration, hoping it's homogeneous. But there is some you need to know the surface concentration there. So in this case, they use the trough, right? So they compress, like a PVT instrument in 2D. It's a pressure area instrument. You can control the thermodynamic state. Okay. So one thing which is important is that, if you think about this when you go swimming later, and lie on the sea, and let's hope the sea is clean, okay? And now you're moving, your friend pushes you forward, right? What you feel is friction on your body, okay, everywhere. Now, if the sea were dirty, which can also happen, those who go swimming in the Seine soon will maybe experience that. I will also have friction coming solely from the interface. So momentum diffuses down, and momentum diffuses to the sides. And the higher the interfacial viscosity or viscoelasticity is, the faster the momentum diffuses at the interface. Okay, and that's what you want, because if momentum diffuses at the interface, you get a velocity profile that is linear. If you are in a mixed condition where part of the interface, if part of the diffusion is down and part of the diffusion is horizontal, you have to solve fluid mechanical equations, right? So here's the Navier-Stokes equation written in cylindrical coordinates. We apply an oscillatory motion, we invoke symmetry, and we use a rheological constitutive equation. In this case, we use a viscoelastic, so we generalize the Newtonian equation for the interface, and we assign a modulus and a loss modulus and an elastic modulus to that. So it's a linear viscoelastic interface. And then I get two non-dimensional groups, Reynolds number, inertia matters. This probe is heavy, you have to be careful. And then this Boussinesq number, which is the surface resistance to the bulk resistance. And we want this number to be large, much, much larger than 1. If it's smaller than 1, it means momentum just diffuses down, and you're not measuring anything of the interface. And so, yeah, you can scale that, solve that. I will skip that. This is what it looks like. These are experiments and calculations. This is the real part of the deformation as a function of the position in the gap. This is the needle moving. This is what we assume. What we want in rheology is a constant shear rate across the gap, right? Because we have a rheologically complicated material. We want the shear rate to be constant. In reality, if I'm at low Boussinesq numbers, the momentum will be confined to a region close to the needle because it diffuses down and a little bit at the interface. So the velocity gradient is much, much higher, okay? And so here's a low Boussinesq number flow. This is the real part of the deformation as a function of the position in the gap. And you see it's nonlinear. Fascinating, right? This is for a viscous interface. The fluid is viscous, the interface is viscous, and the velocity profile is nonlinear, right? How cool is that? You have two lengths, you have two speeds of propagation of your momentum, hence the problem becomes nonlinear. But I always find this fascinating. And we see that the velocity gradient is higher at the needle than here. Even worse for rheologists is this is a Newtonian interface, it's a fatty acid, we know it's Newtonian, blah, blah, blah. There's an imaginary component, an out-of-phase component. The stress boundary condition creates a shift between the bulk flow and the interfacial flow. So even though this should be, all is Newtonian, phase angle should be 90 degrees, nothing special, we see that there's an out-of-phase component. because the momentum transfer has different speeds at the interface and in the bulk. And so I get a phase shift even for a purely Newtonian material, which has nothing to do with material properties. It's just a consequence of the fact that I have two speeds of momentum transfer. And so so you would measure an apparent viscoelasticity. Hey, where everything's Newtonian. Not good. It gets less, I mean, look at the axis. Here it's almost linear at the Boussinesq number of 100. The outer phase component becomes very, very small. And it gets better when you get more and more. But it's a problem when you measure, right? So you're doing an experiment where you're assuming you're oscillating and you're assuming that you know the velocity gradient, but you don't because you don't know the rheological properties of the interface, which you're trying to measure, okay? So what we do is we estimate the Boussinesq number. We say, oh, it's about 10. We calculate the velocity profile, and then we recalculate, sorry, this should be Boussinesq, and we calculate the stresses until we converge, right? And this means here's an example of a system. This was work by Tom. So this is the modulus. If you assume that you know the velocity profile, it was this. If you don't, you correct it. But mainly the phase angle is completely wrong if you don't take these velocity field calculations into account. So you need to iteratively solve for the velocity profile. You're looking at you're measuring a boundary condition of a fluid mechanical problem. The fluid mechanical problem is full flow in 3D, and you want to learn what happens at the interface, and that's a bit of a challenge. And so this is and so there's a bunch of codes now available. I think the people that sell these instruments now even are aware of this, so that's good. Yeah. Anyway, so these are the different techniques. These flow field calculations better. Yes, sorry. Yes, go ahead. Right. There, I'm a certified rheologist. So you check gap effects, you check size effects. So we 3D print rings of different dimensions, and that's what we do. And you know, interfaces are a little bit noisier, so they're a little bit more forgiving. Within the noise, there is no slip. Is there a slip at interfaces? Can there be slip across the interface? Very interesting question that has been escaping us so far. But yeah, very, very good point. But as a good rheologist, change geometry effects. Okay, good. Right. When to trust the data? So, what? Never. So here's a very simple molecule that we measured, and we measured it in this around 20 millinewton meters. So it's a fatty acid. It's in a gas state until about 20 mean molecular area. If you compress beyond that, it starts really interacting. It goes up. It's essentially supposed to be a viscous interface. This is data that we found from different groups. This is data from my lab. It all agreed, but it was different from the. So we started to worry a little bit. So how do we trust data, right? This is the simplest system that you can imagine. It's viscous, etc. So we set out to do an analysis. This with Randy Ewald and Damian Rengley. You are always going to be close to the noise levels of the instruments. For example, if you do the double wall ring on a highly advanced magnetic bearing controlled stress rheometer, you'll be 2 or 3 times above the noise level, which is not a lot. So you really need to do that. So here you see an experiment where we have hexadecanol at 35 millinewton meter. This is the needle diameter, and this is our oscillatory flow. This is the tip of the needle. We know the stress because we know the magnetization of the needle, so we know the deformation because we know the position of the needle, and we can do rheology. Okay? So we can take the signals, stress, in this case current through our coils, position and strain, and then we can Fourier transform them, and you can decide to have a certain noise level that you say, okay, now I know that I'm no longer within the noise. We take 10%, but okay, you could take 5. As long as you say what you're doing, this is absolutely fine. Background, and you say, okay, this is the noise floor, and you can really say, when I'm above the noise floor, I accept this. You can also do this for rotational instruments. They don't always do it properly, the PTA instruments and Danton parts of this world, but some do a reasonable analysis of this. Then we can have inertia. We have very, if you have this needle floating around, moving around on a very, on a monolayer, this can be very complex. And so inertia you see by having a quadratic scaling with frequency and by calculating the inertia of your probe. I mean, this is classical mechanics. Then you do this correction for the subphase drag. This is the error you make again, you have some below a Boussinesq number of say 100. You have to do the analysis. Above, you don't. And then finally, the rings are not perfectly smooth. Here's a very bad one. So you get undulations of the contact line. You get some capillarity. So you get some apparent elasticity, right? And so you can really define operating windows for the different rheometers. Here we went a bit haywire. This is all the different things we had in our lab. We even did a bicone. It didn't work, just to tease Peter a bit. So these are different hexadecanal data. And these are the operating windows which we calculate, and you can really map out, but you basically need different instruments for different things. Not in the, so TA Instruments had the brilliant idea to take a patent of us and try to circumvent it by having the cup moving, and then you do. Normally it's not an issue, it's really the probe. Yeah, the length scales are still small now. Fluid inertia only matters when you're moving the fluid, okay? But you can see, you can measure, and if you overlay these operating windows on published data, you would be surprised. I mean, this is really, the code is available, so you can use them. It's really important. It's a difficult experiment. Okay, good. All right. So we generate relevant conditions. For example, we can have the time-dependent concentration, as you pointed out. This is beer, Westmaler, Feldschlossen, and Hopfab. Hopfab is it's Swiss German for off with your head. That's also what I think they should do to the brewer. Feldschlossen is the beer that the people drink on the train in the 1 liter cans, and then Westmaler is a civilized beer. Much to my regret, the Westmaler, this is the modulus G prime, G double prime as a function of time. So the Feldschlossen actually developed some serious viscoelasticity after some time. Ha! And the Belgian beer did not. So I was utterly and truly disappointed. Turns out it has to do, we'll learn about that on Monday. Yeah. Here's measurements on DPPC, dipolbutylphosphatidylgalena, phospholipid, different concentrations, where you have the elastic modulus, in this case a function of frequency. Within the operating windows, this is, you get orders of magnitude variation. You can compare this to free volume, free area theories, and really see molecular effects, etc. of packing. But the key point is you need to know what's at your interface, okay? That's important. Okay, good. For shear, there's an array of techniques available, and they work. I think we have confidence now on what we really can measure. But of course, we only measure the shape-changing resistance of an interface, which is only part of the story. Nonlinear rheology, there's a little bit with large amplitude oscillations, but I don't think this field is matured yet, and I don't even know if it's relevant, but okay. A big discussion has been, is there a shear viscosity of surfactant? My good friend Todd Squires says no. My other good friend Benoit Scheid said yes. I think it depends on the nature of the chemistry matters here, but you have to be very careful with the measurements. And then structural characterization remains poor, and I think this quote has already been said, rheology without morphology is said to be like theology, and vice versa. There's the opposite as well. But this, having good methods to look at microstructures is difficult. We have Brewster angle microscopy, classical microscopies, grazing incidence, neutron reflectivity, but again, there is little done in combination with mechanical deformations. Good. So shear, we can do very well, but it's not that relevant. If I talk about emulsion stability, if I'm making droplets, I'm trying to create interface, right? If I have coalescence, I have to break a film and compress the area. So the most important deformation mode most of the time is dilation or compression. It's conservation of misery all over, right? The one thing that you want to measure really is more difficult to measure, and and dilatation rheometry is not instrumentally more difficult, but it's conceptually more difficult because now you have mixing of these thermodynamic effects and mechanical effects, and that's annoying. So what are typical geometries for dilatational rheometry? First, you can use the troughs. The troughs can change area, but caveat, if I take a Langmuir-Pockels trough and I change the area, I also change the shape. I go from a rectangle to a square to a rectangle oriented the other way. So it's an anisotropic deformation. So in my lab we built, and also from some Joe Samanyuk, for example, and in Japan there's other groups that made a radial trough, isotropic, or a quadrotrough, shape-conserving troughs. You can keep a square and keep it in a square, a circle in a circle, a triangle in a triangle. That's all fine. And then you have the most popular methods, because everybody has them, pendant drop methods. Okay, so classical method to measure sessile or pendant drops to measure surface tension. Great technique, very easy, but devious. Because when I change the volume of a droplet, I change shape and area size. Here, at the edge of my capillary, when I have a drop, the strain in radial direction is what? 0. It's all axial. Near the bottom of the bubble, or the droplet, there the strain is isotropic. So I have a mixed deformation field, and that is annoying. Mixed deformation fields are annoying. If I have a combination of shear and dilation, and I'm trying to do a measurement of the dilatational properties, we'll see that this is, annoying. Good. So let's look. Flory already pointed out in a paper in the 60s, I wasn't even born, where he said that if I have a trough like this and I do a 2D experiment, he was interested in polymer films and thin layers. And he says when I do an experiment, and depending on the position of my Wilhelmi plate, I will measure different things. As I'm compressing, I will have a change in the thermodynamic state. I will have a bulk compressibility, but I will also have a change in shape, and I will have a shear contribution. So if I hang my plate in this direction, the shear contribution will add to the compressional contribution. If I hang it like this, it will be the negative. And if I use the radial trough with an isotropic, I will only get the surface tension change and then the mechanics, compression modulus. Here you see a polymer, polyterebutyl methacrylate. It's a methacrylate. It's a glassy polymer. You can spread it fairly nicely. I have a surface pressure area isotherm. At high areas, I have a gas. The molecules are individually happy. They're little blobs floating around. And then they bump into each other and form a liquid. And then I have a liquid-solid solution. And I see I have a solid because now I start having a shear modulus. And the shear modulus influences the measurement. So clearly, in this case, the measurement of the plate hanging like this, or a radial geometry, give different results. So it cannot be a state property. It has to be influenced by mechanics, which makes total sense. You're reaching a solid material here. As you have a solid material, you expect there to be a shear modulus and also a compression elasticity. And so this means that mixed deformation fields are annoying, right? Because then you need to know the two parameters, and it depends on the value. This is with a simple model, but it depends on the ratio between K and G, which deformation the system will take. Okay, good? Yeah. Sure, absolutely. So the worst would be materials with a high shear modulus. So networks, gels, 2D interfaces. If I have a low shear modulus, so that depends. And I must say, I don't have that intuition yet on what controls the Poisson coefficient in interfaces. If I have time, which I may give you one example where you even can get auxetic materials with negative Poisson coefficients at the interface. So it's fantastic. Anyway, all the misery of mechanics then comes into play, right? Okay, so let's look at the radial trough. Let's look at our equation that we saw again. Bullock stresses will matter. If I deform very quickly, I will have to do fluid mechanical calculations. Again, it's a planar interface, so this doesn't matter. Concentration is homogeneous. This doesn't matter. It's a flat interface. This doesn't matter. This doesn't matter. So I only have Bullock stresses and then the extra stresses. And if the Bullock stresses are small compared to the extra stresses, I have a pure kinematically well-defined deformation. Okay? Good. Happy, happy. Here you see some data. This is this was for asphaltenes, and this is for silica particles. And you can see that the surface stress versus area, you can even fit it with these models. This is the Neo-Hookean elastic model, so that you can get this data. So there is, in addition to the surface tension change, there is a purely mechanical stress in compression as well. And deconvoluting that can be very difficult, okay? But you get things. This was a system we worked on with Cécile Monteux at the SPCI, which I really like from a didactic perspective. There are two polymers, polyvinyl pyridine PMMA, and by itself, these polymers are not very surface active. Okay, so when we spread one of the polymers and we compress them, they actually go out of the plane. They form loops, and the surface pressure as a function of area does not change a lot. Okay, blue is PVP, red is PMMA. When we combine them and do a layer by layer assembly, and now you get hydrophobic and hydrogen bonding between the layers, so you form effectively a network, and we now compress, what do we get? We get really mechanical stresses, and what you see plotted here are the modulus which we measured from a compression experiment, and then applying the Boltzmann superposition principle, so linear viscoelasticity, the fact that stresses are additive, and it works. So the extra stress has that, okay? There you go. Here's another way of looking at it. This is in a creep experiment in strain. Okay, good. A caveat. This is one of my things that I get nervous about because we're working on this. It's you know, the instruments that are sold and use the Young they use the pendant drop. They use the Young Laplace equation to get the stresses, which is, you know, not good, right? If I have extra stresses, I will need a constitutive equation. And so when you do these measurements for pure surfactants, it's fine. That's all you get. You get changes in surface tension. Okay. If I have protein networks, don't do this. It is going to be a mess because the deformation field at the interface depends on both the compression modulus and the shear modulus. And as you just pointed out, we don't know the relation between those two a priori. So the deformation field that will engender will depend on the properties of the thing you try to measure. And so it's a complicated technique. So the key is that you have to measure the shape and the pressure at the same time. Okay, so if I have pressure and shape, I have enough equations to get the Laplacian and get the contributions to the surface tension, and then get the local deformations. And this has been pointed out by many people, not just by us, right? So especially the group in Sofia, Danov and Petkov, then Niki Denkov, the former prime minister of Bulgaria, so you always have to believe your prime ministers, no, especially the English. No, anyway, you get very things. The thing is that it's a very easy experiment to do, but you have to be careful how to, because all the complexity, all the different contributions that I pointed to can occur here in this experiment. It's conservation of misery all over, right? It's a simple experiment to do, very nice. You push a button, things come out, but the analysis is a mess. You get a mixed deformation field, coupling of shear and dilatation, and you get non-isotropic deformations, okay? And all instruments provide a limited analysis. There's some help if you use the capillary pressure tensiometer, where you just make a hemispherical bubble, where at least you can get at the tip the strains to be uniform and pure dilation, or you have to really do the analysis of the anisotropic strains. It's the same as with the Langmuir tip, but now the strains are anisotropic on a droplet, and we'll see that here. Okay, I'll skip this. Okay, for example, here we do a calculation with a linear elastic module with a K and a G that are realistic, isotropic interface, K 20 millinewton meters, G 10 millinewton meters. And this is the stress, meridional and hoop stress. So meridional is in the long direction, which is most affected by the anisotropy, and then the hoop stress. And then we see how it evolves as we compress our bubble. And you see that the stress, especially in the neck of the system, gets very anisotropic because you get a lot of, I get a lot of shear, and shear is cheaper, half the price. So you can get much cheaper deformations. Here's another example of these polymer multilayers. We make a bubble, we absorb the polymers, we know from independent measurements the shear modulus, we know the equation of state, and then we can do compressions. And when you simply try to fit a Laplacian to this, it will not work, and you will see an error on your fit. But you can fit then these types of models, and you can see this is the Young Laplace stress, and this is the additional stress with a 5% compression, 10% compression, 20% compression, and a little bit more. Okay, and you see that about half of the stress in this compressed bubble comes from mechanics, and half comes from changes in surface tension. Okay, and so you can do that if you measure the stress, the pressure at the same time as the shape, and these codes are available. People do different methods, spectral. You have to measure curvatures. Curvature measurements is always annoying because it's a numerical differentiation, but okay. And there are things working on. Here's some other examples. Here are asphaltenes. They even wrinkle, right? You've maybe seen this if you have proteins and you shrink a bubble, they wrinkle. I mean, it's because you get a buckling instability at the interface. So that before that wrinkling, there is already significant mechanical stress, and you get very deviating ones. These are hydrophobin proteins on air-water interfaces. This is from Danov's work. They also get instabilities, and then this is for the polymer multilayers on a bubble. very anisotropic stresses, right? So the pendant drop apparatus is that. And unfortunately, for oscillatory flows, we don't have the analysis yet. That's being worked on by several people, and we'll see who get there. Okay, skip this. So for dilatational one, conservation of misery, the techniques are not as robust in the sense that they give you clean kinematics, okay? This is really a problem. For soluble systems, we already saw before, we will see a time-dependent surface tension, Lucas and Van den Tempel, and you measure diffusion. For insoluble systems with solid-like behavior, we really see a bulk-like compression modulus or dilatational modulus, which is a material function, strain softening, strain hardening, time-dependent, thixotropic, work hardening, whatever you want, you get it all. Results should be checked for amplitude and size. The question about slip comes up. And there are devices with clean kinematics, the radial trough, and to some extent the capillary pressure tensiometer. So these are now available, and people are building them. There's even code where you can 3D print them and build them in your lab. Many systems will have mixed dynamics, and this is annoying, okay? Okay, to stop, I will show you some mixed flow field stuff. This was my bad idea, okay? So I told my students, group meeting, I have a brilliant idea, which you should never say. Let's change the double wall ring, which we had developed in our group, and let's now, I mean, I know Gareth is a car man, right? You like cars, right? Driving fast. And so I was inspired by the Wankel engine, which is an elliptical cross-section, and if you rotate that, you get compression dilation. And so I first said, let's make a ring that's like a Wankel engine. Students didn't like it. And then Tom made this potato masher thing, 3D printed this. And so if I now rotate this around, on the front of such a asperity, I will have compression, on the back I will have dilation. So I thought it was brilliant. We were going to do dilatational rheology with a rotational rheometer. All my problems were going to be solved. So we solved fluid mechanical equations. And of course, you get this Poisson-like ratio, the ratio between the dilatational properties. We have a viscosity here. We have the compressibility, which are coming from the interface, and the bulk. Okay, and then we did the simulations and we did the experiments. This is, I should have known, right? If you have a mixed flow field, the interface will choose the path of least deformation, okay? If I have a high dilatational viscosity here, this is the dilatational component in the flow field. It is absent because the interface likes to shear locally. Yeah, it can. If I have a low dilatational viscosity, there's plenty of dilatation, but it does not contribute a lot to the stress. So conservation of misery, you know, when you have a mixed deformation field, the deformation that is cheap will dominate, but will not contribute to the stress a lot, so you cannot measure it. So in the end, it's a nice piece of underused equipment in my lab now, okay? The same holds true, and there I want to closely come to an end. The same holds true for microrheology. I will not talk about that, but just, you know, you can use diffusivity to measure viscosity, okay? And this is annoying. If you move a particle in a compressible interface, you know, a microrheological experiment is never going to be a kinematically well-controlled experiment. And the flow field just arises because of that. Now, at the interface, when I have compressibility, when I have Marangoni, and when I have shear, diffusion at an interface is influenced by the dilatational properties because it controls the deformation field around the particle. And so here you see for, again, these different parameters, this is the velocity field, this is the divergence of the surface vector, and this is then the shear component. And you see again the same story. If shear is cheap, I will get a lot of shear. If shear is expensive, not a lot of shear. So the diffusivity is influenced, and this was for driven motions, so imposed deformations, but we have yet to do the analysis for the problem of Brownian motion at an interface. And then there's the coupling to the bulk, so it's a messy problem. So be careful with microrheology, especially if your interfaces are compressible. If you are at the plateau, we've struggled with this with phospholipids, for example. If you're at a expanded liquid condensed coexistence region, the interface is perfectly compressible. So what do you get, right? It's very hard to see what the deformation fields will be. Anyway, good. On Monday, I'll talk a little bit about applying these ideas and using the rheological properties in complex flows. For example, a drainage flow or a thin film flow, and there's different ways to then see how rheology now plays a role in foam stability, but we'll hear maybe a bit about that. And okay, Good. With that, I think I've covered enough material. I had in the notes you'll find some examples of interfacial rheological active materials. For example, colloidal gels in 2D. If you do the compressional rheology, you will see that it's different from the shear rheology, and your Poisson coefficient actually changes with composition, because in these gels you have rotating hinge points which can lead to auxetic behavior. Very cool. And this means that the mechanics of these particle stabilized interfaces or protein stabilized interfaces will be very complicated. But the tools are there, right? And I think we can we can decouple that and then have some predictive power on that. Good. I think that's, let me see. That's what I wanted to say. And with that, I want to thank you. This is where my lab is. Peter is there. He calls me the fool on the hill. That's fine. And with that, I thank you for your attention. Happy to take questions and discuss.